Good afternoon, chemistry class, or good morning, or good evening, whatever time it is that you guys are signing on right now. I miss you. I'm down here in my classroom by myself. Got the whiteboard going. We're going to move backwards. Actually, let me skip back one chapter or one slide. Because we're picking up today on chapter 10, energy. And within this chapter, we're going to talk about the different forms of energy within potential energy and kinetic energy. We'll talk about thermodynamics. We're also going to do some calculations on energy inputs. So how much energy is required to change a specific amount of fluid, like water, or maybe something like the specific amount of energy required to change the temperature of something like iron or gold or silver. So we're going to work through some calorie to joule calculations, some joule to calorie calculations, as well as specific heat. And that'll be our first section that we'll be working on this week. So just a quick little review for you guys. So energy. So if you guys go back to your first year with me for physical science, we talked about energy in the different forms. Two of the main ones within physics and physical science we talk about are potential energy and kinetic energy. And potential energy is all due to position. So usually in physics, we're talking about like a big boulder on a hill, and it has a lot of mass, and it can fall. As it falls, it gains energy in the form of kinetic energy. And when it hits the ground, it takes all that kinetic energy and forms it back into potential energy or stored position energy to where it lands. So there's a transfer of that energy. We also have within potential energy in chemistry bonds that can get broken, things like gasoline or hexane or propane, things like that. When we break those bonds, we release that energy. So potential energy stored due to position or composition, while kinetic energy is all about motion. And though we think about a car driving down the road as kinetic energy, we're going to see too temperature works within kinetic energy. So again, quick little review, law of conservation of energy. Remember, energy cannot be created or destroyed. It just changes form. So you burn a gallon of gasoline in your car, well, you produce a whole bunch of heat. You produce some water, remember, within combustion reactions, some carbon dioxide and other byproducts. But that energy, what you used, if you combined all those little bits of particles and put them back together, it would still be gasoline. You could calculate the amount of energy. So energy in the universe is constant, always has been. But one of the things to think about is when you transfer energy, like in this case, I say throwing a ball, and I'll send the slides to you guys as well. When you throw the ball to somebody, let's say you're playing catch for softball or baseball, and the other person catches it, the energy that you receive isn't exactly the same as when that person threw that. Part of it's due to the friction within the air, but also air molecules binding up around it, which actually causes it to heat up. So we'll talk about that within kinetic energy as well. Work, force times distance. So I want to push a student out of a classroom, and let's say it's a big student, I got to apply a lot of force. Let's say it's a small student, I got to apply a little bit of force. But these are things of which we're talking about transferring energy over a certain type of distance. So if you don't move anything, no work's done. You could push a car all day long and have it not go anywhere. You could be exhausted, but you didn't get your work done. Okay, so one of the things on the bottom of the last slide, sorry to bring up about to, is if you roll a ball down the hill, it's going to lose that potential energy and it's going to change the kinetic energy. But also when it changes that kinetic energy to it hitting another object, it's going to lose some energy due to frictional heat. So that's a lot of the things that we deal with also in life. Your tires making contact with the road, that's a frictional heat loss. So your tires aren't always, there are specific tires for better gas mileage, some that have better grip for being in the mud or sand or whatnot, but you lose some of that heat due to that frictional force. Temperature is just measuring the random motion, average kinetic energy of a substance or a component of substances. And so when you guys are taking the temperature of something in science, in Celsius, what you're measuring is actually that kinetic energy of those particles moving around. The faster they move around, the higher the temperature to use that energy, that change in energy. And that's what we think about as in heat. So heat always goes from high to low. A way of thinking about that, you got a nice hot coffee, you go step outside in ocean shores in wintertime, and that coffee soon loses a lot of heat. Next thing you know, you're drinking lukewarm coffee. And that's because it goes from high to low. The temperature outside is colder than the temperature inside. The temperature outside is colder than the temperature of the coffee, and hence the coffee is going to cool down until you reach an equilibrium and that energy flow will stop. So once that, if it's 52 degrees outside, or let's go within Celsius, 8 degrees Celsius outside, once both the fluid of the coffee and the air temperature equal, that energy exchange will stop. Exothermic and endothermic reactions. We've seen a bunch of these this year within blowing up things and freezing things and talking about those changes in temperatures. But what we're talking about are two things, the system and the surroundings. The system is the part of which we're focusing our attention. So if it was a match or a chemical compound, we're looking at those bonds as well as those atoms that are arranged in a certain specific way, while everything else is in the surroundings. So that could be a book in the room, it could be a plane in the air, it could be a bush outside. But when we talk about reactions in these places, endothermic, we're talking about systems and surroundings. And that's our exothermic and endothermic. So exothermic, it releases heat, while endothermic takes in heat. So if you grab something and it feels cold, it's actually taking the heat from your body, and that's what you sense as it being cold. While you're standing by a nice warm fire on the beach in summertime, and you're, I gotta stand away a little bit, it's a little hot. That's because that heat is being given off to you. So it is heating the system or the surroundings. And last thing before I move on, oops. I'll skip over thermodynamics, but we are going to come back to this, is measuring energy changes. So a calorie is something that we think about a lot of times within food that we eat, but that's actually the kilocalorie. When we're talking about calories in science, we're talking about the change of energy of 1 gram of water by 1 degree Celsius, which is a huge amount of energy. So kilocalories is what you end up eating, but calories and joules are both forms of energy. And so when we look at how we calculate changes in temperature in a bit within water, we're going to look at 1 calorie is equal to 4.184 joules. And that number again, if you go back to your freshman year of science, we'll see that 4.184 number again within the amount of energy for newtons for, with a force of 1 newton for a distance of 1 meter. And that's joules. So remember James Joules, that's who it's named after. That's why we give it the big J. But that's the way that we talk about energy within the system. And lastly, before I close off with you guys and we move on to some calculations, measuring energy changes. So when everything on this planet has a different specific heat, a different amount of energy that it takes to raise its temperature by a gram by 1 degree Celsius. So gold, the amount of energy applied to gold will raise the temperature by 32 degrees Celsius compared to that of water. So gold is what we call a heat sink for a metal. That's why we use it on computers and electronics, because it takes that heat and it dissipates it very quickly. So this is all I'm going to cover right now. The next thing we're going to do is just some calculations within joules to calories and calories to joules, as well as changes in specific heat. So I hope this helps. I'll send you guys a copy, and I hope you're all doing well, and I miss you. Peace.